Okay, guys. We're in the rest of the time. I just like let me tell you kind of the things that we need to know about cardinality. Okay. Okay. So like here's our kind of goals for this section. One, we want to we just want to make sure that like we're using this symbol less than or equal to. We want to make sure that less than or equal to behaves like the less than or equal to symbol should, meaning we want to show that x is less than or equal to the cardinality of x. You know, show that if x is less than or equal to cardinality of y, y is less than or equal to cardinality of z, then x is less than or equal to the cardinality of z. Okay, and I'll put this as a separate point. If cardinality of x is less than or equal to cardinality of y and vice versa, then they have the same cardinality. Okay, then we also want to make sure like finite sets and natural numbers play well together. We want to do stuff like if m is less than n and cardinality of x is equal to the m, cardinality of y is equal to n, then we want to show that like cardinality of x is strictly less than the cardinality of y, stuff like that. Okay. Here, that means that we need to show that there exists a one-to-one function from x to y, but no one-to-one and onto function from y to x. Okay. You know, so we need to show stuff like that. We also need to show, you know, like there's a lot of other things to do. Like, for example, we need to show, maybe we want to look at if the cardinality of x is m, then the cardinality of the power set of x, those should be 2 to the m, things like that. And then there's also the notion of countability. And uncountability, in particular, the real numbers are uncountable. And we also want to talk about cardinal numbers a little bit. Okay. This is what we want from cardinality. Okay, actually, one of the hardest things would be like this first point is we can do it right now. We'll probably do it right now. The hardest point, well, to me, is this is the anti-symmetry of like the less than or equal to for cardinality. And we will try to prove this on Friday. No, sorry, that's the wrong class. Wednesday, yes, much better. Okay. Okay, so let's try and at least tick off this first point. Okay. Let x, y, z be sets. Then the cardinality of x is less than or equal to the cardinality of x. If the cardinality of x is less than or equal to the cardinality of y, and cardinality of y is less than or equal to the cardinality of z, then cardinality of x is less than or equal to the cardinality of z. Good. Again, so definition of less than or equal to means that we have to find a one-to-one function from x to x, and the identity function will work. So that kind of takes care of the first part. Oh, wait, let me just move this up. For part one, define f from x to x by f of x equals x for all x. Then f is one-to-one. So the cardinality of x is less than or equal to the cardinality of x. For part two, suppose f from x to y is one-to-one, and g from y to z is one-to-one. Then g composed with f, which goes from x to z, is also one-to-one. So the cardinality of x is less than or equal to the cardinality of z. Okay, and here now is maybe a good time that we can kind of check that g of f is one-to-one, just as exercise. Suppose g and f are one-to-one functions. Prove g of f is g of f is one-to-one. Proof or / solution. We'd have to remember the definition of one-to-one. We suppose g of f of x equals g of f of x prime. Now, our theorem about g of f says, but g of f of x, that's just g of f of x, and g of f of x prime, that's just g of f of x prime. Okay. Now, therefore, g of f of x equals g of f of x prime, and g is one-to-one. Since g is one-to-one, and therefore x equals x prime, since f is one-to-one, QED. Proving that g of f is one-to-one. Okay, and in my proof, we didn't need to assume that f goes from x to y or g goes from y to z. We just need that both functions are one-to-one, and we get this. Okay. Okay, so now I want to set up Wednesday's class. So we have this. This is what we're going to prove on Wednesday. Let X and Y be two sets. Suppose, you can, sorry. Let me find the last page. Sorry about that. Is that okay now? Okay. Okay. So this is what we want to prove next. Suppose that cardinality of X is less than or equal to cardinality of Y and vice versa. Then cardinality of X equals cardinality of Y. Okay. This is called the Cantor-Schroeder-Bernstein theorem. Okay. And today I just want to see how this theorem is just a corollary of like some lemma. So we're going to state a lemma, use the lemma to prove the theorem, and then we'll prove the lemma on Wednesday. Okay. So let me state the lemma. Okay. Suppose A1 is a subset of B, is a subset of A. Suppose also that the cardinality of A1 equals the cardinality of A. Then the cardinality of B equals the cardinality of A. Okay, now let's use this lemma to prove the theorem. And then on Wednesday, we just have the task to prove this lemma. It's pretty hard, but at least it's not as bad as the theorem. Okay. So let's prove this theorem. We're given f from x to y, g from y to x, both one-to-one functions. Okay. Let's see. Okay, so our situation is f of x is contained in y. And let's look at g of f of x. And that is a subset of x. Okay, so g of x is f of x is a subset of x. So we let a1 be g of f of x. And notice that's contained in g of y, and that's contained in x. Okay, so this is a1, this is going to be b, this is going to be a. Okay, so now clearly the cardinality of a equals the cardinality of, the cardinality of a1 equals the cardinality of a, since g of f from x to g of f of x is 1-to-1 and onto. We already know that g of f is 1-to-1, and it's onto because we've defined the range to be exactly the like g of like what it would mean to be onto. Like we've constructed it to be onto by definition. Okay, so now x and g of f of x have the same cardinality, and in between you have this set g of y. So by our lemma, so the cardinality of g of y would be equal to the cardinality of x. And the cardinality of g of y is just the cardinality of y. So y equals the cardinality of x. Y cardinalities of y and x are the same. Okay. So that means we are reduced to proving this lemma. Which is still going to take a while, but you know, as an application of this lemma, we get this Cantor-Schroeder-Bernstein theorem, which is good to know. Okay, so that is where we can stop today. Thank you again. For being here. I guess I'll see you guys on Wednesday. And I will also have assignment 5 for you. Well, quite short assignment 5 anyways. Later today. Okay. Okay, bye everyone.